All right, well, so be it. So first thing I always do in lectures is ask, do you have any questions at all about anything? The quiz solutions are up on the, on OneNote. Did anybody look at them? All right. It was meant to be a replica problem. I literally put up the dimensions of that problem and everything on the board. The only thing that changed was the B field, and you just had to do the derivatives correctly. Y'all with me, class? All right, so now without further ado, now our next game is New Mexico State, is that right? Here.
Yeah.
What time though?
3 in the PM.
That actually is a great time. All right, now on Friday, let me just tell you this. So this Friday, I'm planning to give a quiz. Y'all hear me? I'm planning to give a quiz. It is going to be on the material I covered today and Wednesday related to propagation. And it's important that you please keep up with this. Now, the reason I'm saying this, in my opinion, this is where people really get shot in the foot. They have a lot going on. They have projects, everything like that, and they put this on a back burner until finals week, and then they don't even know what to ask. They get that confused. And I'm not kidding about this. So this is not something, I don't think they go through this in detail in physics. They do talk about the general wave equation, but this is real important, okay? Now, if you want to know where it is in the book, this is not chapter 6 yet, but it does. The thing about it is the end of chapter 5, beginning of chapter 6, all cover the same material. So what we're going to do is this. I try to be as clear about this as possible. This is section 5.5 on page 305. It's Maxwell's equations. I'm going to do this different than his book. He has you grind through some very arduous calculations to prove to yourself something. I don't think you need to do that, but you do need to pay attention to this. Now, these two equations you have to know very well for the final exam. The two Maxwell's equations, they're the curl equations. So the first one is curl of H is equal to J plus the partial of D with respect to P. These are the general forms. And the second is going to be curl of E equals minus dB dt. I'm going to put these down. I think you know what this is. I kind of go over this over and over. What do we call this equation? Whose name do we associate with it? Ampere, right? Ampere's law. You all remember this class? What about this one? The curl of E. Michael Faraday's law of induction. These are the two biggies, all right? Now, James Clerk Maxwell came along and he created a single equation with single unknowns that literally defined electromagnetic propagation in any reference frame, including relativistic reference frames. So, with these two things, these are in the time domain. That's the general form you see almost everywhere. It's the general form of the equation. Generally, they're correct. Not any coupling factors, so we say B is equal to epsilon E. That is simply the relationship between B and E. We talk about J is equal to sigma E. That relates actual conductivity, or the ability of charge to move in some material, the electric field and the current density. And finally, you get B is equal to mu H. So these are I call them coupling equations. They relate all the different terms to each other. One other I'm going to put up here is divergence of B is equal to the volume charge density, and that lends itself to divergence of E is equal to rho V over epsilon. I'm putting these here just so you see everything on the board. I wish I had those boards you can shove up and down, because I could have these equations there and just reference them all the time. Y'all with me, class? Now we're going to start here, and here's what I'm planning on doing. I'm going to take that from the time domain general form. I'm going to make substitutions so we have equations with just E and H. I don't know if I did this completely yet. I think I've put all this stuff down before. Then after that, I'm going to get one equation with one unknown, and I'm going to do it in the frequency domain. I don't want to do it in the time domain because it gets a little, it's too complicated for unnecessary reasons. So here's my plan. First, I'm going to take this equation and I'm going to replace J with sigma E and D with epsilon E. So the first equation, I'm going to take curl of H, and I'm going to say this is really sigma E plus, and then it's going to be epsilon times the partial of D with respect to T. I hope everybody sees I'm just taking the definitions I have above and replacing these terms. Y'all with me, class? Just write this down. Try to appreciate the fact that I don't want to confuse anybody. I'm just telling you exactly what I'm doing and the fundamental reason why we're going to get one equation with only one unknown section. Now, at this point, I'm going to take this equation and I'm going to replace B with mu epsilon. So then you get curl of E equal to minus mu times pH dt. Now I have equations, excuse me, that's E. I have equations with just just E and just H. Y'all with me, class? Got two equations with just two unknowns. Now, the next part of it is straightforward. And I always try to bring back, I try to reference things you've seen over and over again. Back in circuits, do you all remember if you had an inductor and you said that there was a voltage V across that inductor and a current I was going into the terminal, the positive terminal, and you could say L times VI dt, right, was equal to the voltage that would be measured. Do you all remember that, class? How many do? LVIDT was the voltage. That's the time domain form. Technically, really, it should be V is equal to the time derivative of the quantity L times I. Because there could be a time change in L, but usually not. In other words, the inductor has a singular value, it doesn't change with time. Now, when you go to the frequency domain, that very equation becomes V is equal to J omega L times I. And I think everybody remembers that. Y'all, how many remember that? Right? We call that the impedance right here, J omega L of the inductor. It's the ratio of voltage to current. Y'all with me, class? What really went on there is you went to the phasor domain. The simple relationship is this. And a lot of people don't have a firm grasp of this, and they mess up on the final when I ask for a time domain form. If you have any phasor quantity, we'll use voltage. So voltage is a phasor, it has some magnitude, and it has some angle. You can also render it as V naught e to the J theta. Does everybody remember that? You would get like 10 volts at 30 degrees in circuits problem. Y'all remember? That's phasor. The relationship from the phasor quantity to time, actually, it's just a tilde, not a vector, is V of t was the real part of e to the j omega t times v phasor. If y'all remember that, and generally speaking, what happens is you get the real part, and then it's going to be e to the j omega t times v naught e to the j theta. I'm doing this one more time. You would combine the exponentials, right? You get e to the j omega t plus v. Y'all see this, class? Then you would use Euler's identity. Here, I'll do it one more time. You would say v of t here would be the real part of v naught e to the j quantity omega t plus the phase angle. And you would use Euler's identity, e to the j theta is cosine of theta plus j sine of theta. Now that's one of Euler's identities. Y'all follow me on this, class? How many remember Euler's? At least me putting it up. You have to know that stuff very well. Now, here's my point here. When you take the real part of just e to the j omega t, or e to the j theta, it's only the cosine term. You all see that? The j indicates an imaginary component. So when we take the real component of this, we get a cosine. And we get v of t is equal to v naught times cosine of omega t plus the phase angle. Now I'm doing that one time because I'm about to go to the phasor domain, and I want you to appreciate the relationship between the phasor and time domain. You all with me? Believe it or not, that right there, a lot of people don't remember well. If I say, what is the time domain form of the voltage? And I give you a frequency domain problem, something where you have like J40 ohms plus 30 ohms in series with a voltage of, say, 10 at an angle of 30 degrees, and I want the current in the time domain, they will not understand how to get it. Do you all follow me? Now, we've had that some time ago, but usually Dave Irwin's book and the way he teaches, usually he just stays in a phasor domain, he doesn't bring it back to the time, so you don't have that like familiarity with that. You all with me, everyone? Just remember that. So now going to these two equations, I'm going to take them both in the phasor domain. And you remember, or into the frequency domain. Anytime you had a DDT in the phasor domain, or in the time domain, it became simply a j omega in the frequency. How many remember that? Right? It's all based on what? You're assuming everything varies as e to the j omega t. So you take a time derivative of e to the j omega t, you get a j omega coming out. Y'all see this, class? Okay, I come over here. This first equation right here therefore becomes curl of h equal to sigma e plus, and this is going to be just j omega epsilon times e. You all see, the only thing I've done there is take the time derivative, replace it with j omega. Everybody? Take a good look. I hope you can see it back there. You guys are so far back. I can't believe it. You can't see it? Your eyes are so much better than mine. I can barely see you. All right. We get this, right? Did you have a question? It's all right.
Oh, I was just wondering, is that like beta E or sigma?
Where are you looking?
Or J omega?
It's j omega epsilon, and epsilon is epsilon relative to epsilon naught times e. Now, the next equation right here is going to become curl of e equal to, and it's simply going to be minus j omega mu times h. Now I've got everything. I've got h and I've got e, and everything's in the frequency domain. Now I want one equation with one unknown. I don't know if I've done this in this class. I'm trying to remember. Anybody have an idea how you can get that? Think of the mathematical operators: curl, divergence, gradient, Laplacian. What would allow you to create one equation with one unknown? I bet you see it. Afraid to say it. What if I take another curl of this one? Just listen. So I'm going to take curl of E equal to minus j omega mu curl of H, right? Hear me, everyone? Hey, there's a curl of H here. It's only in terms of E. Y'all see this, class? Everybody? So if I take another curl of this one, this is how it's done in the book too. This is in chapter 6 and at the end of 5. Is equal to minus j omega mu times curl of H. All right, now I replace curl of H with that first equation, Ampere's law. And I get this equation. I'm going to erase all that over here so I can continue. So I come over here, and now I have curl of E, and it's equal to minus j omega mu times curl of H. Well, that's curl of H, so I go ahead and put sigma, and I'll factor out the j omega plus j omega epsilon times E, and that's a single equation with only E, even though there's two curls in there. Do y'all follow me, class? Now, why did I want to do that? It's another question you probably are wondering about. The reason is we're going to get solutions to this because these are differential equations. They're spatial and frequency domain operators, but frequency domain operators, for all intents and purposes, are just like constants if you have a spatial differential equation. Do y'all follow me? We're going to get general forms of solutions for these things for specific assumptions. Everybody with me on this? Now, there's one thing I don't think you know is, maybe you do. If you look at this curl of E, this is a vector identity. The curl of E can be rendered as the gradient of the divergence of E, and it then becomes minus del squared of E. This is a vector Laplacian, it's not a scalar. I just want to comment on that. Some of you will remember this because in the future you're going to see if it's a vector Laplacian, it has three components. It's not a scalar like voltage. The voltage is scalar. There's only one component of the derivative. This has three. There will be three general terms for that, which means three separated equations in general for that. And it's equal to, and this, what we do, I'm going to go ahead and do this. It's going to be minus, well, I'll tell you what, I'm going to do this. This actually becomes minus gamma squared times E. Then up here, make note of this. Gamma is equal to alpha plus j beta, and it's equal to the square root of j omega mu times sigma plus j omega epsilon. Now, that right there, gamma, is called the propagation constant. Don't let this scare you. I just want to make sure you understand one thing. Do you remember when we did transmission lines? We created a constant that I labeled gamma. How many remember that? Right? Gamma had a real part that had to do with attenuation, alpha, and it had an imaginary part, beta, that had to do with the wave number. It is the same here for propagating electromagnetic energy. Okay? Everybody? I'm just trying to give you some context to this. I'm trying to show you the similarity. Now here, this equation, we can start working with. We have to make some assumptions to get anything meaningful out of it in a way that is something applied to the real world. The first thing we're going to assume here is rho v, the charge density, is equal to 0. That's an assumption. Now, why would I make that assumption? Well, actually, for most propagating phenomena, like in the atmosphere, in space, almost any place in the normal sense that we see propagating electromagnetic waves, like FM radio stations, anything like that, you can make that assumption. It's a very valid assumption. But why would I do that? Take a look at that. What might that do for me? If rho v is 0, what might that do for me over here? Can you all see that? Divergence of E is rho v over epsilon. If rho v is 0, divergence of E is 0, right? Can anybody see this? Why would I do it? Because that first term goes away, doesn't it? Can you all see it? The gradient divergence goes away. Everybody with me? So now I can say, based on that, I have minus, well, really, I'll take the del squared to the other side, so I have del squared of E, and it's going to be that minus gamma squared of E is 0. I'm just showing you. I'm getting rid of things based on that assumption allows me to do that. I just got one equation, one unknown. It's really a second order spatial derivative, but it's a vector right here, vector Laplacian. Now that, the del squared of E is a much different form in Cartesian versus cylindrical versus spherical. And in general, the only one you care about initially to get a feel for this is going to be actually Cartesian coordinates. We're going to assume something called a plane wave propagation. Does anybody have a question? If you got a question for me,
Yeah,
yes,
I just
sir.
got a little one. Is that delta E minus delta squared E? Or are you saying
What are you talking about?
right there on that, where you're pointing, yeah.
That's the gradient of the
Gradient.
divergence. This is a divergence operator. That is a gradient in front of it. So it's a vector. Remember, each of these terms has to be a vector. You can't have a scalar and a vector added.
Yeah.
All right? So that, I'm telling you these things because this is exactly how it's done in the book without, you might say, a detailed explanation. I'm trying to make it simple to understand why we're doing everything. We're doing this to find a form of the equation that we can solve and it's meaningful. Now at this point, we're going to use that to get the form of wave propagation in the atmosphere for something called a plane wave. Now I'm going to erase all this and come back over here. I continue on, I gotta ask this. Do we have a men's basketball game this week?
It's away. Well, it's a neutral site game.
All right, but there's nothing here on campus for men's basketball.
Yes, sir.
Okay, I'm just checking, I'm thinking about parking problems that I may face shortly. I don't know if you guys have the same problems I have, but when there is basketball games, that lot next to the rec center gets blocked at 3 o'clock. And I like to know that so I can get there at 2:45 and still get a workout and get out of there before the whole place goes nuts. That's the only reason. Back to this. Now we do this, we're going to assume plane wave phenomena. So I gotta explain this. Plane wave propagation. So, I'm gonna try to do this as simple as possible. And I like to draw analogies to simple things you understand. So think about this, if electromagnetic phenomena that's propagating is going to be likened to wave phenomena on the surface of a liquid, say if you drop a pebble into a puddle. This is a similarity I want to draw. So if you drop a pebble into a puddle, you can see these rings where a wave will have a constant, or something where you're going to have the only variation in the amplitude of the wave will be radially outward. It'll be a function of time and radial distance. You all follow me? You drop a pebble, these ripples stretch. You leave time go by, and all of a sudden, maybe a long way off, all of a sudden, the radius of that circle is getting very large, and it looks pretty much like the wave is planar. It doesn't have any curvature. Do you all follow me on that, class? Which means, if you took a look a long way away at the difference in the amplitude versus any portion of that wave, would be the same, and it's propagating in only one direction. That is a plane wave. What it means is that we're going to talk about electromagnetic phenomena that's a long way from the source. Call it an antenna. Long, long way. So the wavefront itself doesn't vary over a surface that's perpendicular to the direction it's propagated. Can everybody imagine that? Remember, electromagnetic phenomena, when it propagates, the E field and the H field will be perpendicular to the direction of propagation. And we're going to assume, because of that, there will be no variation in the spatial derivatives of the E field with respect to that plane that it's in. In other words, if it's going in the Z direction, then the derivative of the electric field with respect to X or Y at a given point will be 0. Do you all follow me on this, class? Some of this takes time to grasp. So based on that, I'm going to take this equation, and I'm just going to, you don't have to write this part, but I'm going to comment so you understand. In general, if we're talking about Cartesian coordinates, the del squared of E operator becomes really del squared of, and it's really going to be of EX, AX. So you take the AX component, this del squared operator has 3 components. Take derivatives, second derivatives with respect to X, Y, and Z of E of X. Then it's going to be plus del squared of EY, AY, plus del squared of EZ, AZ. And these del squared operators have 3 derivatives that are second order, X, Y, and Z derivatives. You don't have to write that down, just appreciate what I'm going to say. Now we're going to assume plane wave propagation, but we're going to assume propagation, actually we get rid of all this and just get to the point. We're going to assume plane wave propagation in positive Z direction. All right, so the waves are propagating in the Z direction. And I'll show you where this is in the book so you can get a better idea. All right, page, this is chapter 6, but it's a better drawing. Yeah, on page 328, figure 6.2, if you have your books, he'll show you what I'm getting at. He's showing you an electric field that is polarized in the X direction, and it's propagated in either the positive or negative Z direction. We're assuming propagation only in the X direction. We go further. And we're going to say the electric field will only have a Z component, I mean an X component. We'll only have some, call it EX in the AX direction. So that means it's oriented in the X direction, but it's propagating in the Z. Y'all follow me, class? It will not have any variation with Y or X in terms of the magnitude of E of X. This takes a bit to get used to. Now I'm going to come over here and I'm going to take this equation, and because of that, this del squared derivative, I'll do it right here. It becomes simply the second derivative of E of X with respect to X squared, or I mean Z squared, pardon me, Z squared, minus gamma squared EX equals 0. I'm doing that for a reason. I'm going to comment and so you can get a handle on this. A lot of this is foreign, I know. It takes a while to really appreciate this. That's a vector equation. This is a scalar equation. We're assuming the E field itself, we're only looking at the EX component. So that's literally a scalar. We could put a vector next to this, AX, and say it's a vector equation, but we don't need that. Y'all with me, class? If we look at this, that's a single equation. It's a second order differential equation that's homogeneous. The solution is well known. I got a question for you. I'll write it over here, but once you have that, if I have that equation, the second derivative of EX with respect to Z squared minus gamma squared EX equals 0, I'm just asking you this. I don't worry if you don't know. But how would you solve that? Say your boss is talking to you in an interview, or your possible boss, and he throws this down on a piece of paper. How would you solve that? You can ask these kind of questions.
Differential equation.
Pardon me?
It's a differential equation.
It is a differential equation. How would you solve it for the closed form
Laplace.
solution?
A Laplacian transform.
A Laplace transform is perfect, right? That would do it, right? The del squared brings out an S squared. It's a spatial derivative. But this is one thing I don't think they really emphasize. Everything you learned about Laplace transforms was really time and S domain, right? Wasn't it?
Yeah.
It can be X, it can be spatial as well as S. The transform domain does not require it to be time. It can be spatial, it can have X, Y, Z, it can have rho, phi, theta. In other words, it can have any coordinate as long as you can perform a transform on it by the definition of Laplace. You can go into the S domain, solve it, and then bring it back and do partial fraction expansion. That'll work. What's the other way to do this? You all had differential equation.
Quadratic formula.
Well, I think I know what you mean, but it's what? You could use an integrating factor or the assumed solution because it is a homogeneous differential equation. As you assume the solution will have the form some constant, call it A, e to the lambda, and then you would put if it varies with Z, you would put Z there. Do you all remember doing this? And you'd go ahead and do the derivatives on that, 2 derivatives, and see what the solution is. How many remember that?
So, wait, are you talking about separation of variables, or are you talking about putting in
No,
general
separation of variables is for
Yes.
differential equations that have X, Y, and Z components.
Yeah,
That's
so
later.
yeah.
This is nothing more than this. Here's what you're doing. And I don't really want to go through this. Let's assume EX itself is some constant A, E to, and we'll just call it lambda Z because it's a function of Z. Y'all with me, class? Can you all see this? All right, take 2 derivatives of that because I need that. Well, then I get 2 derivatives of this. It's going to be what? A lambda squared, right? E to the lambda Z. You all see this? I'm just showing you the way you were taught, I think. I hope this is the way you were taught. Do y'all remember doing something like this, right? Take that and plug it in there. What happens? Then I get A times lambda squared times e to the lambda z, that's this term, minus gamma squared times, and then you just take the original assumption, a e to the lambda z equals 0. Do y'all follow me, class? This is kind of a classic way. It's a homogeneous differential equation. They have a name for this. Isn't it just called using not an integrating factor, but it's the recursive form. I forgot the name of this thing. They probably have different names. Do y'all see what I've done there, class? How many do? Now, what do you notice about that? Well, the a goes away. This goes away. Now I have this, right? So how does that factor? That's why. Lambda minus gamma, lambda plus gamma, right? You agree with that? Equals 0. Right? So what is lambda? It's plus or minus gamma. Isn't it, class? You all see that as a solution? And that's the way you were taught to do it. How long ago was differential equations? 3 semesters, 2 semesters?
What semester are we in? Fall,
Beats me.
spring. That's a good, yeah.
You had this, right?
It was this year. We took it this year.
No, it was last year.
We took it in the fall?
I think you.
Got me on this one. You had it, right?
Yeah, last year. I think last
Was
year.
it junior year or sophomore year?
It was in the spring.
Last fall? It's recent. You may not have used it, but that's,
Yeah, you're right.
but I do this with Laplace.
Oh, and in
Whoever
school.
said Laplace is right, that's how I do it. All right.
What's my name?
Now, here's what it means. It means the solution of this differential equation is going to be the e of x will be, and write this down. Matter of fact, let me put it here. The solution will be e of x equals some e naught of x, and then put a little plus there, e to the minus gamma z plus e 0x minus e to the plus gamma z. I want to make sure I say this is e gamma times z here, gamma times z. Y'all with me, class? It's real important to remember this. When we did the transmission line problems, do you remember we had a solution, v naught plus e to the minus gamma z plus v naught minus e to the minus gamma z. How many remember that? All right. One of them was propagating in the plus z direction, the other was propagating in the minus z direction. How many remember that? If you don't, trust me, it was true. Put a little arrow here and put plus z. This component is going in the positive z direction, thus the plus on that e. Can you all see that e by the way back there? All right. This is going in the negative z direction. Everybody with me? I'm making some points here that are going to be very important later on. Now, that's the frequency domain form. You'll know this is completely general. We're assuming propagation in the z direction, and the E field only has an x component. This is real important to see. I'm going to now take it into the time domain. All right, so to find E of the E field as a function of both z and t. Remember, that right there is a function of z. But to bring, it's still in the omega domain, isn't it, class? To bring it back to the time domain, we have to say we'll take the real part of that E field, and I'll put e to the j omega t here, times that E field, E x tilde. Now I'm going to talk my way through this part. Well, I'll put it down. You'll see. This is going to be the real part of, and here I have e to the j omega t times ex, or e0x plus e to the, and that gamma is going to be e to the minus alpha plus j beta z, and it's going to be plus e to the 0x minus e to the plus j alpha plus j beta and the quantity times z. Now I just wrote that down. I literally took that and stuck it in there, but I expanded gamma as alpha plus j beta. Follow me, class? Just try to focus right here. Now when I take the real part, you'll notice I get e to the j omega t times e to the minus j beta z. Do you all see that? The e to the minus alpha z is no, it's going to come right out in front. So when we do this, we end up with this. We get ex0 plus e to the minus alpha z, and then you're going to get a cosine of omega t minus beta z plus e x0 minus times e to the gamma z, and it's going to be times cosine of omega t plus beta z, and that is the E field as a function of z and t. And in his book, he'll have this, because he's always assuming propagation in the z direction, either plus or minus, and he'll have the form of propagation, in the time domain, it'll be a cosine. And if I can find it. Actually, that thing is on page 323 and 324 that I showed you about with the differential, or how to solve the differential equation. Trying to give you best reference I can find for this. Well, right now. Oh, here it is. Look at page 324, equation 6.26. Y'all hear me? Equation 6.26. Just take a look there. Y'all see it? How many have the books? How many have access to the
Which equation number was it again?
6.26? It's on page 324. Y'all see it? Yep. That's the equation that dictates propagation in the time domain. Usually we don't use this, but write this down and take this is going in the plus z direction. This is propagating in the minus z direction. This is just the E field. Y'all follow me, class, on this one? I want you to take a look. Y'all with me? Some of these things, why do we need to know this? You're going to need to know this for a lot of reasons. Basically, because we're going to have to be able to calculate the E field values, gamma, alpha, which means alpha and beta, all these things for given parameters and problems. You'll see this more in a second. Now that's just the electric field. This is the form. That's the this is the frequency domain or phasor domain form. This is the time domain form for electric field propagating, plane wave propagation, where the E field's going in the x direction but propagating in the z. Now, next, I'm going to leave that up there. We're going to go ahead and get a bunch of information. Matter of fact, from here, just from that equation, we're going to get some stuff that's valuable. Let me see if anybody gets this. What I want to do, let me get rid of that too. This eraser's fantastic. Another one of my other classes. Now, I'm going to talk about this in a way that hopefully makes sense to you. What we try to do is define things of importance. Velocity is very important. You agree with that? Usually you think of speed of light as the limit. Well, actually, in many media, especially dense gases, or you might say materials, it's not just the speed of light. It has to be adjusted for the actual material you're going through. Speed of light is as fast as it gets, though, for any kind of energy propagation. But if we look at this, let's just look at the positive z-directed portion of that waveform. Now I have Ex right here. I would just call it Ex plus is going to be some E, not X plus, times e to the minus alpha z times cosine of omega t minus beta z. And that's the x component. Does everybody see that? I just rewrote it, right? Can you all see this? How would you get the velocity that way? Phase velocity, that gives you a hint. Anybody? If we graph this, just give yourself a second to think about it. If we took this waveform and graphed it versus z, and call this ex for t equals 0, it would look something like this. And it would be, based on the value of alpha, this would be decay. Do you all follow me on this? The t equals 0. If you let time go by a little, and say this is going to be for t equals, I don't know, say omega, I'll just call it t prime. T prime greater than 0. It'll look like this. What I'm trying to do is draw you basically the same waveform, only displaced with time. You'll notice the peak moved a given distance, delta z. Can you all see that? For a given delta t. Can you all see that? It gives you a hint. How would you get the value of the actual velocity? Well, it's a phase velocity is what I'm talking about. You all see that this is really a phase point. That's at 0. The argument omega t minus beta z would be 0. This is at omega t minus beta z is 0 as well. You all follow me? But it's a time advanced. So if you wanted the phase velocity, you look at the phase. The phase itself is a function of time and space. Is just equal to omega t minus beta z, right? Now, if that's the phase, if we take a derivative of that with respect to time, then we find out an equation where we would like to set that equal to 0. We don't want any change in the phase with respect to time. So we take a derivative of phase with respect to time and set it equal to 0. Derivative of this with respect to time is just omega. Derivative of that with respect to time is minus beta dz dt. You probably see where I'm going with this by now. dz dt is a velocity, isn't it, class? Like dx dt or any other form of a spatial variation with time. How many see this? You're professional. You're good professional engineers, electrical engineers, electrical and computer engineers. It's important you see this fairly well. So we call that the phase velocity, dz dt. And that means the phase velocity itself is equal to omega divided by beta for plane length. You remember me doing that before for transmission lines? How many do? A couple of people, yeah. This is real important. This is the phase. It's how fast this crest of the waveform will move. It's really important to see that. And you'll notice one other thing. It's a function of both omega and beta. All right, it's not just one. Okay, now, after that, we're going to go ahead and get the H field and the relationship between the H field and the E field, which is called impedance, intrinsic impedance of the medium. And I'll leave that there. So I'm going to try to do this the way he does it in the book, and I'll give you a reference. So this is going to be, I could do it out of chapter 5, but he really complicates it with a whole lot of matrix math that's unnecessary. If you look on page 324 and 325 in your book, this is section 6.1, you're going to find interesting information. Now, I'm going to stay in the phase domain, and I'm assuming only we're talking about the plus z portion of the plane wave propagation. So I get the E field in the phase domain equal to some E naught x plus E, and I'll call it minus gamma z, and that's the E field, and I can put AX in. With me, it's propagating in the Z direction, but it has an X sense to it. That's its orientation. Everybody with me, class? If you're wondering about what that means, think about a mechanical analogy. Suppose I have a rope and I secure it to that wall and I'm holding it. And I do this. You'll see the you'll see the actual rope deform, and there'll be a variation in the height of that rope versus time and space. It'll be moving that way. Just think about it, right? It's actually being displaced in a direction perpendicular to its propagational direction. Y'all follow me? It's the same thing with electromagnetics. The E field is in this direction, but it's propagating in that direction. Got me on this one? Okay, if I take this as such, and now I know that what? I know that the curl of E is equal to minus J omega mu times H. Do y'all remember that? Now I'm in the phase domain. Remember me doing that? Faraday's law of induction. I replace B with mu H and take the time derivative and turn it into J omega. With me? Now, if I do the curl of E on this, yeah, I'm about over time. What's going to happen is that minus J gamma, the minus J or minus gamma is going to come out in front. I'm just trying to get to the bottom line. But what you're going to see, if you do the curl of E and then orient it right, you're going to find that H will not be in the X direction. It'll be in the Y direction. And it will have the form of E 0x, and it's going to, well, tell you what, I'm trying to hurry this one up. Let me show you where it is. And I think I'm out of time. Am I out of time? All right, so what I want you to do is look at what he does on page 324 to 325. But he finds the ratio of E to H, and it's called beta. I'll do this next time. I'm going to ask you to read that, and I'll give you some homework. I don't want to just put up something that's going to confuse you. But at this point right here, if you take this E field, you do the curl, you will get the form of the H field, and it will be in the Y direction. It'll be perpendicular. Actually, the H field itself, my form, is going to have a value E not X over something called beta that I'll explain in a second. It's called the intrinsic impedance. It'll be E to the minus gamma Z, and it will be in the AY direction. That's what this curl is going to lead to. And I just put down that eta naught is equal to the square root of J omega mu over sigma plus J omega epsilon. I did not have time to prove that, but I will. Okay, see you on Wednesday.